In today's video, we're going to discuss about Venn diagrams and different operations on sets. Before starting about different operations on sets, we'll first learn about Venn diagrams. So Venn diagrams are the pictorial representation of different sets where we generally use circles and rectangles to denote different sets. So generally, the universal set of a given data is represented using rectangles, which is followed by different overlapping circles present within the universal set, which represents different sets. So let us, for example, take three sets A, B, and C in the universal set U. So here these three sets are represented using circles, and the universal set is represented using a rectangle. So basically, Venn diagrams are graphic charts made of overlapping circles where each circle represents a different set. Venn diagram provides a clear way to express the relationships between different sets, which in particular helps in the visualization of data easier. Now we will discuss about what are the different types of operations on sets. So unlike normal arithmetic or algebra, in case of sets, we cannot use the regular operations such as addition, subtraction, multiplication, or division. In case of sets, it has different sets of operations which we are going to learn about now and express those operations in terms of Venn diagrams. So in all the cases, let us take two arbitrary sets A and B, and let us learn about what are the different operations possible on these two sets. The first operation we are going to learn about is called union. So the union of two sets A and B is denoted as A union B, which represents a set which consists of all the elements which are present in A or B or both. That means for any element X that belongs in A union B, this should imply that X belongs to A or X belongs to B. If this is expressed in a Venn diagram, then we can express it as follows. So let us take two sets A and B in the universal set U. The shaded region denotes the set of A union B. Clearly, the shaded region has all the sections of set A as well as set B, along with the section which is common to both the sets. So for any element present within A union B, it must be either a member of A or B or both. Now, the union of two sets can be better understood using an example. So let us take two sets A, which consists of the elements 1, 2, 3, 4, and 5, and let us take a set B, which consists of the elements 2, 4, 6, 8, and 10. Therefore, the set of A union B will have all the elements present in both the sets, but the elements which are common to both the sets must be written only once. Therefore, A union B has the elements 1, 2, 3, 4, 5, 6, 8, and 10. The next operation that we are going to learn about is called intersection. The intersection of two sets A and B is denoted as A intersection B, which is a set comprising of the elements present in both A and set B. Therefore, for any element X that belongs to the set of A intersection B, then it must be a part of A as well as B. Hence, the set A intersection B consists of all the elements common to both set A and B. Now, from the definition, it is clear that if an element X is not a member of the set A intersection B, then either it does not belong in set A or it does not belong in set B. The intersection of two sets can be represented in a Venn diagram as follows. So let us take two sets A and B inside the universal set U. The shaded region between A and B, as represented in the diagram, represents the set A intersection B, which is the common portion between both the overlapping circles. The intersection of two sets can be better understood using an example. So let us take the same sets A and B consisting of the elements as taken earlier. Therefore, A intersection B is a set which consists of all the elements common to both the sets A and B. Therefore, A intersection B consists of the elements 2 and 4. Based on the definition of intersection, the sets can be further categorized as two different types of sets. The first type is known as disjoint sets. So if two sets are such that they have no common elements between them, that is, the intersection of the two sets is equal to 5, then the sets are said to be disjoint sets. However, if two sets are such that the intersection of those two sets is not equals to 5, then those two sets are called intersecting sets. The next operation that we are going to learn about is known as the difference of two sets. The difference of two sets is represented as A minus B or A difference B, which is a set which consists of the elements which is present in A but not in B. Therefore, for any element present in the set A difference B, the element must be a member of set A as well as it should not be present in the set B. This can be expressed in the Venn diagram as follows. So let us take two sets A and B present in the universal set Q. Then the region shaded in the diagram represents the set A minus B. From the diagram, it is clear that the region of A minus B is equal to the set A minus the region which is common to both A and B. This can be better understood using an example. So let us take two sets A and B consisting of the elements 1, 2, 3, 4, 5, and B has the elements 2, 4, 6, 8, and 10. Therefore, the set A minus B will be a set which has all the elements which are present in A but not in B. Therefore, A minus B will have the elements 1, 3, and 5. The next operation we are going to learn is symmetric difference of two sets. The symmetric difference of two sets is denoted as A delta B, where it is a set that comprises of the union of the sets A difference B and B difference A. This set can be expressed in the Venn diagram as follows. So let us take two sets A and B present in universal set U. Then the region of A minus B is this shaded region, and the region of B minus A is this shaded region. The total shaded region represents the symmetric difference A minus B union B minus A. From the Venn diagram, it is clear that the symmetric difference of two sets can also be expressed as the difference between the set of A union B and the set A intersection B. Since from the region of A union B, if we take out the region of A intersection B, the remaining portion describes the set of A symmetric difference B. Hence, A delta B can also be expressed as A union B minus A intersection B. This can be further demonstrated using an example. So let us take two sets A and B consisting of these elements. Now, A minus B will be a set which has all the elements in A but not in B, and B minus A will be a set which has all the elements present in B but not in A. Therefore, A symmetric difference B will be the union of the sets A minus B and B minus A, which gives us the set 1, 3, 5, 6, 8, 10. The next operation is called the complement of a set. The complement of a set A can be represented various ways. Few of the ways are A bar or A dash or A complement. The complement of set is a set which consists of all the elements which are present in the universal set but not present in A. Therefore, A complement can also be written as the difference between the universal set and the set A. From the definition, it follows that if an element X belongs in A, then it will not belong in A complement and vice versa. The Venn diagram for A complement can be expressed as follows. So let us take a set A in universal set U. The region between the universal set and the set is shaded, which describes the set of A complement. This can be better understood using an example. So let us take the universal set as all the natural numbers from 1 till 10. And let us take a set A which consists of the elements 1, 2, 3, 4, and 5. Therefore, A complement will be a set which consists of all the elements present in the universal set but not in set A. Therefore, A complement will have the elements 6, 7, 8, 9, and 10. Now, there are a few results that we need to know about complements. Complement of a null set will always give us the universal set. And in the same way, the complement of the universal set gives us the null set. The complement of any set gives us that set back. The union of a set with its complement gives us the universal set, and the intersection of a set with its complement gives us phi. We are now going to discuss about a few laws of operations on set, starting with the idempotent law. The idempotent law states that for any set A, which is a subset of the universal set U, the union of the set with itself gives us set A, and the intersection of a set with itself also gives us the set itself. The second law that we are going to learn about is known as the identity law. The identity law states that for any set A, which is a subset of the universal set U, the union of a set with the null set gives us the set back, and the intersection of the set with the universal set also gives us the set back. The next law called the commutative law. Now, we have learned about the commutative law in previous classes, and here the commutative law has the same definition. So for any two sets A and B, where A and B are both subsets of U, the union of these two sets are interchangeable. So A union B can be written as B union A. This is the law of commutative for union of sets. Similarly, the intersection of two sets can also be interchanged. So A intersection B can be written as B intersection A, which is the commutative law for intersection of sets. However, it needs to be noted that commutative is not applicable for difference of two sets. So A minus B is not equals to B minus A. The next law that we're going to learn about is the associative law. So for any three sets A, B, and C, associative law states that A union B union C is equal to A union B union C. This is the associative law for union of sets. What it means is that if we find the union of sets A and B first and then find the union of the result with C, that will give us the same set as finding the union of B and C first, after which we can find the union of the result of B union C with A. A similar result can be obtained for the intersection of two sets. So A intersection B intersection C can be written as A intersection B intersection C, which gives us the associative law for intersection of sets. The next law that we're going to learn about is called the distributive law, and this is one of the most important laws in set algebra. So for any three sets A, B, and C, where every one of them is a subset of U, the union of a set on the intersection of two sets can be distributed. So here it can be written as, first we can do the union of A with B and write it as A union B. Then we can do the union of A with C and write it as A union C. And the operation that was happening between the sets B and C, that comes in the middle. So we can write it as A union B intersection C is equals to A union B intersection A union C. This is the distributive law of union over intersection. A similar result can be obtained for intersection over union. So let us take, for example, A intersection B union C. This can be further written as A intersection B union A intersection C. This describes the distributive law of intersection over union. The next law that we are going to learn about is called the De Morgan's law. De Morgan's law discusses about different results of complements on union and intersection of two sets. The first law states that A union B whole complement is equals to A complement intersection B complement. The second law states that A intersection B whole complement is equals to A complement union B complement. Now, De Morgan's law can be easily proved using the theory of subsets. So what we will do here is, first we have to prove that the set in the LHS is a subset of RHS. To do that, let us take an element X which belongs to A union B whole complement. If X belongs to A union B complement, that implies that X is not a member of A union B. This means that X does not belong in A and X does not belong in B. However, if X is not a member of A, then X must belong in A complement, and if X is not a member of B, then X must belong in B complement. This means that X must be a member of A complement intersection B complement. So here we see that for any element present in A union B whole complement, that same element is also a member of the set A complement intersection B complement. Therefore, we can say that A union B whole complement must be a subset of A complement intersection B complement. Similarly, let us take another element Y, and let us assume that Y is a member of the set A complement intersection B complement. This implies that Y belongs in A complement as well as in B complement. However, if Y is a member of A complement, that implies that Y does not belong in A, and if Y is a member of B complement, that implies that Y does not belong in B. Hence, we can say that Y does not belong in A union B. From this, it can be said that Y then belongs in A union B whole complement. Here again, we see that we have taken an element from the set A complement intersection B complement, and we have proved that the same element also resides in the set A union B whole complement. Therefore, it can be said that A complement intersection B complement is a subset of A union B whole complement. Now, the two results obtained from equation 1 and 2 opposes each other. This means that A union B whole complement is a subset of A complement intersection B complement, as well as it is also the superset of A complement intersection B complement. The two results are satisfied and proven to be true if and only if the sets are equal. Hence, from the results obtained from 1 and 2, we can say that A union B whole complement is equal to A complement intersection B complement. A similar method can be used to prove the second law of De Morgan's. Now, talking about different laws of operations on set, we will establish a result which is not specifically a law on the operations on set. However, we will use this result significantly while solving different problems. And the result is A minus B is equals to A intersection B complement. The way to prove this is using the same method we used to prove De Morgan's law. So let's take an element X and let us say that it belongs in the set A minus B. That means X belongs in A and X is not a member of B. However, if X is not a member of B, then X must belong in B complement. This implies that X is a member of A intersection B complement. Since we have taken a member from the set of A minus B and shown that the same element also resides in the set A intersection B complement, therefore we can say that A minus B is a subset of A intersection B complement. Again, taking an element from the set of A intersection B complement, so let us take Y belongs to A intersection B complement. This implies that Y is a member of A and Y is a member of B complement. However, if Y belongs in B complement, then Y is not a member of B. This implies that Y belongs to A minus B. So here again we see that an element from the set of A intersection B complement resides within the set A minus B. Therefore, we can say that A intersection B complement is a subset of A minus B. Now, the two results are contradicting each other, since in one case A minus B is a subset, whereas in the second result A minus B is a superset. Therefore, these two results will be true if and only if the sets are equal. Hence, A minus B is equal to A intersection B complement. Now, finally, there are a few important results based on the cardinality of sets which can be derived from Venn diagrams. So, let's take two sets A and B present in a universal set U. Now, since we have learned about the Venn diagrams for the union, intersection, and difference of two sets, based on those results, we will now derive a few formulas on the cardinality of sets. So, the first formula is for n of A union B. If we shade the region of the set A followed by shading the region of set B, we see that while adding the members present in the sets of A and B, we have taken the region common to both twice. To remove that anomaly, we have to subtract the region common to both once. So we subtract the cardinality of the set of A intersection B from the sum of cardinality of sets A and B. That will give us the shaded region of A union B. Hence, we can say that the cardinality of A union B is equal to the cardinalities of sets A and B minus the set A intersection B. It follows that if the sets are disjoint, then A intersection B will be a null set. Hence, n of A union B will be 5. In that case, n of A intersection B will be 0. And in that case, n of A union B will be equals to NA plus NB. Following the result of n of A union B, we can also derive two formulas for n of A minus B. Now, n of A minus B can be written as n of A minus n of A intersection B. Similarly, n of B minus A can be written as n of B minus n of A intersection B. Both of these results can be easily understood from a Venn diagram. So let us take a universal set U and two sets A and B present in that universal set. The region of A can be shaded as such. Now, if we erase the shaded region of A intersection B, we are left with this shaded region, which clearly specifies the set A minus B. Hence, we can say that n of A minus B is equal to n of A minus n of A intersection B. In the similar way, we can also show using Venn diagrams that cardinality of B minus A is equals to n of B minus n of A intersection B. Now, in case of three sets, the union of the three sets A union B union C, the cardinality of such a set is represented using the formula NA plus NB plus NC plus n of A intersection B intersection C minus the cardinality of the sets A intersection B plus n of A intersection C plus n of B intersection C. This completes all the results that can be obtained from the Venn diagram of two or more sets. Thank you for watching. Check out the link to submit your questions for future solving sessions in the description box below. Make sure you subscribe to the channel and follow for more such videos. And I'll see you in the next one.